Lab 1 Constant Velocity. The purpose of this lab is to create a computational model of an object traveling in constant motion using the video analysis tool Tracker. The lab addresses the fundamental principle of Newton's second law, or equivalently, the momentum principle. Newton's second law states that the velocity of an object can be found using this equation. Newton's second law further implies that if the net force on an object is zero, its velocity is constant. This equation can then be used to update the position of the object over time. First, we're going to look at the video analysis completed in Tracker. Then we're going to look at a GlowScript code that was written using the information found in Tracker. Then we're going to analyze the computational model given by the computer code. Lastly, the computational model is going to be compared to the Tracker model. To begin the lab, I needed to take a video of an object traveling at a constant velocity. I decided to take a video of a tennis ball rolling on a hardwood floor. Before beginning the analysis of the ball's motion, a few key pieces of information needed to be identified. First, the diameter and mass of an average tennis ball were inserted into the program. Then the system was identified as the tennis ball. The coordinate system was established with the positive x-axis pointing to the right. The video was then trimmed in order to assess the motion that best exemplified a constant velocity. Using the data table, the initial time and position can be identified. The initial velocity of the object can also be identified using the first two data points. Here's the calculation and final result. Scrolling down to the bottom of the table, the final time can also be found. These initial conditions will be used in the computer code used to create a computational model of the object's motion. So let's look at the code. We begin by looking at the part of our code where we can input our initial conditions. The mass was changed to be that of an average tennis ball. The initial position vector and the initial velocity vector were also inputted into the code. Looking at the next section, the while loop was changed to run through the final time of the dataset. The net force vector was set to 0 in order to coincide with Newton's second law. These two equations were also changed in order to accurately represent the equations set forth by the momentum principle. This equation confirms Newton's second law because if F net equals 0, the ball's velocity does not change. Now we can run the code in order to analyze the computational model. This model accurately shows the ball moving in the positive x direction. It expresses the lack of external forces as well as constant velocity, which confirms the application of Newton's second law. We can confirm that the object is moving at constant velocity because the graph of position versus time exemplifies a constant positive slope. Now all the resources are available to compare the observed and predicted position of the object. As you can see, the computational model overpredicts the motion of the object. This is most likely due to the presence of unaccounted forces acting on the tennis ball, such as friction. In order to account for this error, I could have picked a different chunk of time from the original video that better replicated our assumption of constant velocity. The what-if question asks how our results would change or remain the same if we were to flip the axes. Recall that the coordinate system was set to have the motion of the ball traveling in the positive x direction. Our resulting graph looked something like this, representing a constant positive velocity. If we were to flip the x-axis, the resulting graph would instead look like this, representing a constant negative velocity. Although the graphs look different, the slope of the graph remains constant, solidifying the assumption that our object is moving at constant velocity. The what does it mean question asks if it is possible to determine all of the forces acting on the object. While one could argue either answer, I'm going to argue no. Thinking about the complexity of the universe and its interactions, it is impossible to determine every single force acting on the tennis ball at a given moment. While we can think locally and determine the forces of friction and forces that relate to air resistance, it is almost impossible to determine the small gravitational forces exerted on the tennis ball, by heavenly bodies in outer space, for example. To recap, this lab used Tracker to create observed data for an object assumed to be moving at constant velocity. and a computational model from a GlowScript code in order to create predicted data for the object. These models were compared, and it was discovered that it would be difficult to replicate the motion of an object moving at constant velocity in real life due to unaccounted forces. The fundamental principle of Newton's second law was applied when creating the computational model. Observing the motion of an object at constant velocity solidifies the principle set forth by Newton's second law and creates a deeper understanding of this fundamental physics concept.